Good afternoon to all. Today is the revision class of Polymer Chemistry, chapter 13 of Engineering Chemistry syllabus. I hope all other chapters learning materials have been provided to you through Google Classroom. Also, these learning materials have been uploaded in the Institute website. These are some of the questions of this chapter which I have collected for you. These are previous semester questions. And as you see, most of them are short answer type questions. Only define, calculate the degree of polymerization, and write the preparation and use of some polymers. Like this questions are also expected in this semester. If questions come like this, the first question you see, what is a polymer? Give two examples of linear polymer. And in this slide, answer is already there. A polymer may be a natural or synthetic macromolecule comprised of repeating units of smaller molecules. So this itself is the definition. So smaller molecules are monomers and the macromolecule is the polymer. So you can give some of the examples. These are synthetic polymers, starch, cellulose, protein. These are also what natural polymers, biomolecules. And the process is polymerization. From monomer to polymer, the conversion process is polymerization. Some of the monomer and their polymers are listed here. From ethylene to polyethylene, vinyl chloride to polyvinyl chloride or PVC. From glucose to starch, cellulose, glucans, amino acid to proteins, polypeptides. These are macromolecules and all these are the monomers of such macromolecules. If we categorize them, this can be natural polymer, semi-synthetic polymer and synthetic polymers. Natural, all of you know, these are available in plants and animals, and some of the examples are proteins, cellulose, starch, resins, rubbers. Semi-synthetic ones are actually the polymers which are derivative of natural polymer. For example, cellulose acetate is derived from cellulose, that's why it's semi-synthetic. Synthetic polymers, already you know, we are synthesizing it in laboratory, in industry, like nylon, terylene, synthetic rubber, and vinyl's rubber, polystyrene. These are synthetic polymers. Polyethylene is prepared from ethylene molecule in presence of radical initiator. Radical initiator can be peroxide or aliphatic azo compounds. These are the repeating units. And you know already the polythenes, where you are using it in your daily life, we are using as polythene sheets, carry bags, bottles, and some pipes. So polyethylene has a range of usage in your daily life. You can give n number of examples if such questions come. And later also we will come to the methodology, how low density polyethylene and high density polyethylene are prepared, what is the difference between them, and what are the uses of low density polyethylene and high density polyethylene. Later we will come to that. Teflon is another polymer, and Teflon means it's a polymer is polytetrafluoroethylene. The monomer unit is tetrafluoroethylene. Another polymer you see polyvinyl chloride. The monomer unit is vinyl chloride, CH2 double bond CHCl. And this PVC is also in your daily life you are using it, and all of you are aware of this. Pipes for household, tanks, medical packaging, municipal and industrial applications are there. Electrical cables. So these materials are made up of PVC. Now see another classification: linear polymer, branch chain polymer, and cross-linked or network polymer. Linear polymers are straight chain, so there is no branching. But branch chain polymers, there are certain branching at different sides. And in linear polymers, the examples are high density polyethylene, PVC. In branched chain polymer, the example is low density polyethylene. In low density polyethylene, actually in the chain itself, there is certain branching at different sides. Cross-linked polymers are actually very rigid and hard polymer. It has good mechanical strength. The examples are Bakelite and melamine. We'll come to that. See the pictorial notation, linear polymer, these are the straight chain. In branch chain polymer, there is certain level of branching at different sides. Cross-linked or network polymers is a network-like structure. Now see again another classification, addition and condensation. I think in our classroom activities, we have done many examples of addition and condensation. Here, briefly we will go through them. In addition polymer, what happens actually? Monomers containing double or triple bonds. These monomers combine in a repeating fashion to make the polymer. Example is the PVC and the polyethylene. Whereas in condensation polymers, these are formed by the combination of monomers with the elimination of small molecules such as water, alcohol, hydrogen chloride, etc. Like these small molecules will release in these chemical reactions. And the example is nylon 6,6. This is the best example which what you can write in your exam, semester exam. The examples you see, addition polymerization, vinyl chloride is the monomer and this is the repeating unit. Acrylonitrile is the monomer, then polyacrylonitrile. These are the repeating units. Styrene to polystyrene. In condensation polymers, this is the reaction between adipic acid and hexamethylene diamine. You see in this reaction, because of condensation, one water molecule released. Now you are getting a compound known as nylon 6,6. So nylon 6,6 is the polymer of both these adipic acid as well as hexamethylene diamine. Again coming to another short answer type question which may come like write the difference between homopolymer and copolymer. You already all of you have understood in your classroom activities. This A means it's one of the monomer unit. So the same monomer unit is repeated in the chain. That's why it is homopolymer. If there are two or more than two monomers which chemically combine and after combination this whole unit repeats AB, 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 then this is copolymer. So copolymers are polymers composed of more than one kind of. So nylon 6,6 is a copolymer, whereas PVC and polyethylene these are homopolymer. So again you see this, you can write this as homopolymers because the repeating unit is the same. Same monomer is repeating throughout. One of the synthetic rubber is polychloroprene and the common name is neoprene. So if the polymer is neoprene, then its monomer is chloropene. Chloropene, you see the structure 2-chloro 1,3-butadiene. This is Buna N rubber. Similarly, Buna S rubber 1,3-butadiene plus styrene. So these are also addition polymerization because these two monomers are added to each other to give another polymer. There is no condensation, no release of smaller molecule. These kind of polymerization actually what catalyzed by a peroxide or Ziegler-Natta catalyst or condensation polymer you can see. Adipic acid plus hexamethylene diamine it gives nylon 6,6. This reaction is very important. These polymers have same types of monomer units. You just write one point in the homopolymer, then corresponding point in copolymer. Composed of two or more different kinds of monomers, it is copolymer. Homopolymer formed through addition polymerization, whereas copolymers formed through either addition or condensation. These often have simple structure, but copolymers often have complex structure. Then you can give examples in this side and examples in that side. And some examples of homopolymers are polyethylene, PVC, polypropylene, Here you can give examples of copolymer, nylon 66, polyester, protein. Then some, as I have already told you, some numerical questions also may come. Calculate the degree of polymerization. Suppose molecular mass of a monomer is provided to you and average molecular weight of a polymer is also provided to you. Then you can calculate the degree of polymerization by just mw by mo. Sometimes the mass of monomer may not be provided to you, but the monomer's formula is given to you. Suppose ethylene, PVC. Then you have to calculate the molecular mass of that monomer and just divide here. In the denominator, you put that here. I think so many questions I have given you as a homework. All of you have done it. But again, you have to practice that. Thermoplastic, thermosetting plastic. Actually, if you see the examples, then you can easily differentiate thermoplastic, polyethylene, polystyrene, PVC. Whereas thermosetting plastic are Bakelite, urea formaldehyde. These are rigid cross-linked network polymer, and thermoplastic are simple straight chain polymers. So, what are thermoplastic polymers? These are the linear or slightly branched long chain molecules which often soften on heating and harden on. So if you heat it, it becomes soft. Then once it is cooled, it becomes hard. These polymers possess intermolecular forces for attraction, intermediate between elastomer and fiber. So the mechanical strength is intermediate between elastomer and fiber. The examples are polyethylene and polystyrene. In thermosetting plastic, these are cross-linked and heavily branched molecules which on heating undergo extensive cross-linking in molds and again become infusible. These cannot be reused. So once you heat, again it cannot come back to its original state. Examples are Bakelite and urea. Elastomers are actually rubber or rubber-like solids with elastic properties. In these elastomeric polymers, the polymer chains are held together by the weakest intermolecular forces. These weak binding forces permit the polymer to be stressed. So a few crosslinks are introduced in between the chains which help the polymer to retract to its original position after the force is released. This process is known as vulcanization. So elastomers mostly are rubber-like substances which you can stretch. But to enhance its mechanical strength, you have to introduce some crosslink so that it can again stretch and come back to its original position. The examples are Guna S rubber, Guna N rubber, Neoprene. All these are the examples of elastomer. So, natural polymer or natural rubber. Polyisoprene is a natural rubber where the monomer unit is isoprene. 2-methyl 1,3-butadiene. 2-methyl 1,3-butadiene. This is the isoprene unit. If you polymerize it, it will become polyisoprene. But you have to enhance the mechanical properties of polyisoprene. So one process and the best process to do that is the vulcanization. You have to introduce some sulfur atom inside the different chains. Sulfur forms a bridge between individual polymer molecules when heated with rubber. Often a catalyst and initiator is added to accelerate the vulcanization process. The cross-linked elastomers have much improved mechanical properties and are very durable. You see, this is one straight chain of polyisoprene, this is another straight chain of polyisoprene, and in between two different chains we have introduced sulfur, so that once you bridge different chains it becomes a network structure and its mechanical properties are being enhanced. And a detailed schematic reaction is displayed here. You see one layer plus another layer plus sulfur, so you are getting sulfur bridge, sulfur cross linkage. So this process is known as vulcanization. What is the advantages of vulcanization? Once you vulcanize the natural rubber, now it has good tensile strength and extensibility. It has excellent resilience That is, it turns to the original shape when the deforming load is removed. So it comes back to its original position. It possesses low. So these are the advantages of vulcanized rubber. Better electrical insulator, resistant to organic solvents, and it is useful in wide temperature range. So even minus 40 to 100 degrees centigrade. In this range also this can work. Now we'll come to the preparation and use of selected polymers that are provided in your syllabus, that PVC, polyethylene and Bakelite. PVC, as all of you know, this is made of vinyl chloride. You have to add catalyst, then under heat and pressure. Heat means the temperature should be 40 to 60 degrees centigrade, and some catalyst, like radical initiators like pour acids, pour suppose benzoic acid or some azo compounds may be taken as catalyst to prepare polyvinyl chloride. What is the properties of this polyvinyl chloride? These have insulating properties. That means this is a good insulation material. This has durability. This has good mechanical properties. This has also chemical resistance. That means PVC is resistant to all inorganic chemicals. It has very good resistance against diluted acids, diluted alkali, and aliphatic hydrocarbons. So, because of such properties, these have a range of uses. Like this is used in building and construction industry to produce door and window profiles, handbags, raincoats, pipes. That means in municipal systems also, wire and cable insulation, medical device, medical packaging. So these are a range of uses which PVC has. So you can see some of the pictorial representation. These cables, actually the coverings, these are made up of PVC. This medical packaging are also made up of PVC, and pipes. These are being used in municipal system, in agriculture. So all these materials are made up of PVC. Polyethylene, as I have already told you, there are low density polyethylene and high density polyethylene. And low density means the density of that polyethylene is 0.91 to 0.94 gram per centimeter cube, and above that it comes high density polyethylene. So to prepare these two polyethylenes, we have different methods. For low density, we have to perform the reaction under this temperature, 350 to 570 Kelvin, under pressure of 1000 to 2000 atmosphere, and in presence of catalyst dioxygen or vapor oxide. But for high density polyethylene, 6 to 7 atmosphere pressure, temperature of 330 to 343 Kelvin, and Ziegler-Natta catalyst. This catalyst is being added to prepare high density polyethylene. So what are the uses of polyethylene? You know already the reaction, this is ethylene molecule to polyethylene, and in presence of Ziegler-Natta catalyst you get the high density polyethylene. What are the uses? Packaging film, trash and grocery bags, agricultural molds, wire, cable insulation, squeeze bottles, toys, all these household materials are also made up of polyethylene. Low density polyethylene has certain properties like melting point between 105 to 115 degrees centigrade. Density is this much, and it has good resistance to alcohols, dilute alkalis, limited resistance to aliphatic and aromatic hydrocarbons. These have excellent electrical insulating properties also under low water absorption. So these materials you see, these are made up of low density polyethylene. Some seeds, these polyethylene grocery bags, and these water bottles. But for high density polyethylene, these are melting point 120 to 140 degrees centigrade, and density is much more than LDPE. And these are the properties: excellent resistance to most of the solvents, very good resistance to alcohols, acids and alkali, moderate resistance to oils and grease, poor resistance to hydrocarbons. These have higher tensile strength, excellent electrical insulating properties and very low water absorption. And these have a wide range of applications like crates, trays, bottles for milk, fruit juices, caps for food packaging, jerry cans, drums, and different containers for industry, garbage containers, housewares, and also you see in fibers and textile industry these are being used to prepare ropes, fishing nets, sports nets, and nets for agricultural use, and some decorative fabrics also. And these kind of strong pipes and some bottles, these cans are made up of high density polyethylene. Next, coming to Bakelite. Bakelite is made up of two monomers, phenol and formaldehyde. Phenol formaldehyde polymer, that's why its name is phenol formaldehyde polymer. These are the oldest synthetic polymers. These are obtained by condensation reaction of phenol with formaldehyde in presence of either an acid or a base catalyst. So, as I already have told you, this is a rigid three-dimensional cross-linked network structure, and it is used for making combs, phonograph records, electrical switches, computer disks, and handles of various utensils. Now coming to its preparation, and directly already you know what are the steps. Directly you can go to the reaction. First, phenol plus formaldehyde in acidic or basic medium. It will give ortho and para products. In phenol, you see in ortho position there is a CH2OH and para position also CH2OH. After this substitution, you take selectively this product again in acidic medium. It will give a straight chain compound which is known as novolog. And this novolog again on reaction with formaldehyde, it will give Bakelite, which is a three-dimensional polymer. So there is a bridge of CH2 CH2 methylene bridge between different layers. So this is a three-dimensional polymers. At a time you can see this is the whole step. Ortho or para hydroxy methyl phenol. This product will form. Then selectively you take one ortho product and you get novolog. Again from novolog you react to treat that with formaldehyde to get Bakelite. So this whole step you have to write in your exam when it is asked to write the preparation and use of Bakelite. So this reaction actually it carries much more marks. The handles of utensils and this material, this is the phone, old kind of our landline phone, comb, and these are door seats. These are made up of what? Bakelite materials. So now you can easily answer these questions, whatever have been asked in your previous semester examinations. Thank you very much, and we'll stop here.